In this video set, we're going to go over chapters 8, 9, and 10 just to go through a few last pieces of things that we need to wrap up with. So some of the content in these chapters goes way more in depth than we will for this course. You'll do that in Math 99 instead, and even in Math 141 for some of the things. So just do the things that look the most simple if you're going on your own and reading through things. So here we have rational expressions to start with in chapter 8. You're on page 109 of your workbook. So first we're going to look at reducing rational expressions, but we need to know what they are first. Rational expression is a ratio of two polynomials, a fraction where the numerator and denominator are polynomials. Now remember, a constant could be a polynomial too, by definition. So if we have something like this for 8.1a, 4v plus 2, all divided by 6, that is a rational expression, and we can plug values in. You've seen this, like kind of like formulas you've seen. Plug values in and figure out what the answer is, and that's called evaluating. Now this part is just going to be a good review of fraction work for you and evaluating as well. One thing we want to really be clear on though is that the denominator on here would be undefined if it were 0 on either of these. Like for letter B, where we have an n minus 3, 3 could never be a value of n because that would make it be 0 in undefined situations. So we would say the domain on this one would be n is an element of all real numbers such that n is not equal to 3. So we have to figure out what n is not going to equal. And then I put these little braces around to be for the notation that it's a set. One thing I want to say is that a lot of times we just do this shortcut here and not equal to 3 and just make sure we make a note of that. All right, so before we go into this, I want to show you the graph. I'm going to look up Desmos here, and I've typed in a parent function, we call it, of 1 over x. This is a typical rational function, and this is what it looks like. So I just want you to see that. If we were to put in 1, we would get the value 1, 1. If we put in 0, we would get an undefined situation. So what's happening here is we're approaching the x equals 0 right here, that line x equals 0, which is the y axis, but it never quite touches it. The same thing here, so make it just a touch bigger. You can see how it gets closer and closer and closer. So it's getting to be a really tiny number. The bigger y gets, the smaller x gets. And likewise over here where we have the right hand side, that's approaching the x-axis, so that's our horizontal asymptote at y equals 0. So you'll learn more about asymptotes and all that good stuff in Math 141, which is our pre-calculus. Now if I changed this to be get that to change to x squared, then I have this situation here because I'm always going to get a positive y value. I won't get any of the negatives. I can also put like an expression up in there, right? And sometimes we might have that. Like I'll put the 1, let me pause it, and I'm going to type in the one from our worksheet right here. I'm going to type in this so that you can see what that looks like. Okay, so this one's a little weird because it doesn't have the same shape as the others, right? So I think what happens here, you'll see later when you're in pre-calculus, is that this x minus 3 divides into that. It can be simplified down to a linear So I would end up with just this, it would end up being the x plus 2. So what happens though at that 3, which is what I wanted to show you, maybe I can blow it up even a little more. When x is 3, we are going to have what's called a hole. Here's x is 3. And if I put my pen on there, you can see that's really hard for me to get it right on there. There, I got it for a second. Undefined. Okay, so we always need to remember there's a hole, and usually you see a hole or you write a hole in on the graph. If I had it a little bit differently, let's try one. Let's just change this number to be like 7. And then this is what the graph would look like. So it has that same general shape. There's a slant asymptote, which again you'll learn about later, but I just want you to know what these things are and why we are doing this skill work that we're doing, because we need to find values, we need to find where the hole is, we need to find zeros, we need to find all sorts of good stuff about them. And we are going to just start with plugging in values. So this is somewhat review actually for you guys. So if we plug in 4 here, we're just going to now calculate, and we would get 16 plus 2 over 6. That would be 18 over 6. And then that reduces down to 3/2. So a little fraction review there. On this one here for B, we have n squared minus n minus 6 all divided by n minus 3. So we're going to plug in 4 because that's the value they're interested in. 4 squared minus 4 minus 6 all divided by 4 minus 3. Then we're going to just simplify down. You can do this along with me, pause the video and just check it after. So we end up with 12 minus 6, which is 6. Now we're going to look at finding excluded values of rational expressions. So I'm going to show you when we have a denominator that's 0, how we need to write that and exclude that from what's called our domain. Domain is just anything that x's can be, or sometimes we write it, if there's just one thing it can't be, we write it as all real numbers except such and such. So on this first one, example 8.2, we want to set it equal to 0. I actually suggest, because we're not finding the actual asymptotes, which is what the denominator would be on that problem we looked at earlier. We would have an asymptote, so we write that as a line, and we do want the equal sign. But on this one, we want it to be not equal to. So we want to say the domain is anything. So it's all real numbers except where z plus 5 equals 0. Okay, so now we're just going to solve out when z plus 5 equals 0. That would be all real numbers such that, that line means such that z is not equal to negative 5. Okay, so that's my domain. Now, for that one, it was nice and easy to figure out. You could even just eyeball it. But what's going to happen is we need to factor these. So that's one reason you learned a lot of that factoring. So if I have this situation here, t squared minus 2t minus 8, all divided by t squared minus t minus 12, I can't tell when it's going to equal 0 right off the bat. I'm going to have probably 2 different numbers, oftentimes, unless it's a perfect square trinomial. So let's factor them. And then sometimes things reduce out. But right now, we're just going to be looking at the denominator. So again, we want all real numbers such that t squared minus t minus 12 does not equal 0. So we're going to factor this. So it would be t minus 4, t plus 3. Okay, so we want all real numbers such that they don't equal 0. And then it's going to be a 4 and a negative 3. So my domain is all real numbers such that t is not equal to negative 3 or 4. Okay, now actually I want my brace on the other side of that. There we go. Now this one, maybe you could try it on your own and see, or think about it. You really don't actually have to do any work on this one if you think about it. But if we're looking at all real numbers such that x squared plus 6 is not equal to 0, we're not going to get any real solutions. So it's because of this square here, we're good. This is going to always be positive. Or, yeah, and it will never equal 0. So our answer for that one is just our domain is all real numbers. You could write it in interval notation like this too. Negative infinity to positive infinity. I just wanted to show you really quickly what that expression looks like as a graph in Desmos. So I typed it in using x because that's what Desmos likes. So we have x squared minus 2x minus 8 in the numerator over x squared minus x minus 12 in the denominator. And you can see here where when x is the negative 3, it doesn't touch. Okay. And when x equals 4, that's actually going to be a whole. So if we make it bigger and we pinpoint that, see where that's undefined. It showed for a second, but just so you get the idea, if you were to put 4 in there, you would have an undefined situation, so we would have a whole. Okay. So now we're going to go back to simplifying. And again, rationals look like this. We have non-zero polynomials, and pk over qk is a rational expression. Then we can simplify out. If we have like factors in the numerator and denominator, we can simplify. Just like that b is. So that's actually where you're going to end up having a whole. So for example 8.3, we have 9x to the 7th over 15x cubed. And you've done this skill before, just simplifying. So that comes out to be, reduce this, you'll get 3/5 for your coefficient. And then x to the 7th minus 3 is x to the 4th. So this is a good review of a lot of skills. So try this one as classwork and see how you do with that. So we have 15a cubed b squared, all divided by 25a b to the 5th. And our answer is 3a squared over 5b cubed. Okay, so now we're jumping up to page 111 in your workbook. So it's example 8.4. We can reduce rational expressions with polynomials, but we first need to factor. Be really careful never to do this, like, oh, an x and an x, and I can just slash it out, or 2 goes into 6 3 times. We never want to do that. You always have to factor first. You can only reduce factors with factors. For the numerator and denominator. When they're separated by plus and minus, you can't do it that way for when you have a division operation. So the first thing we're going to do is we're going to factor this numerator to be x plus 3, x minus 2. So hopefully that's coming pretty naturally to you right now. These are pretty easy to figure out because there's usually going to be a match for you, so that's kind of nice. So now on this one, it's a little trickier. 2x squared minus 5x plus 2, so we know we have a 2x and an x. And then the 2 and 1, so I'm going to guess that it's going to be x minus 2. And then this would force to be 2x minus 1, and then check it. We would get negative x, and then a minus 4x, which gives us that middle term. And now what happens is these reduce out. That means there's a hole there. I have a 0 over 0 where there's a hole in the graph. Okay, so then I end up with my answer being x plus 3 over 2x minus 1 for my simplified version of the graph. So if I were to plug values in, I would get the graph. I could plot it out, or I could type that into Desmos, but I do need to actually realize if I just typed this in, I'm not going to get the best picture because I'm not going to see where my hole is. I need to always keep in mind, and this is kind of entry level, so it doesn't have you do this, but you need to keep in mind that x cannot be 2. It can also not be 1/2 from this too. Okay, that you can see clearly in the simplified version, but this you don't see clearly from the simplified version, so you really have to track it. Okay, so try letter B. Do this one as some classwork. And then I think that's it for our purposes for this. It just gives you a good little review of factoring. If you want to do more, you can, but I just want to expose you to what's happening in your future class, just give you a little leg up and do some good comprehensive review along the way. Okay, so this factors to 2 times 5 minus x over 4x times x minus 5. Now, a quick way to factor this is if you know you have like this kind of vice versa situation there with the 5 minus x over x minus 5, it does just equal negative 1. This is y over here because you're factoring out a negative 1. If you want to just do it the long way, that's fine. So then when I reduce, I get negative 1 over 2x. So negative 1 over 2x. Maybe I'll extend this line just a little further. And then make sure you state the domain. X cannot be 0 or 5. Okay? Because from up here, we need to look back at the original. We can't have a 5 in the denominator. That's where there would be a hole in the graph. All right, so that's it for that section. Let's look at multiplying and dividing. You can also do that operation. Again, this is review for you guys, just thinking about multiplying and dividing rational expressions with monomials. So you've done this before. We just didn't pinpoint that this was, a rational. We didn't call it out as such. So the process is the same when you have polynomial over a polynomial. Remember, constants can be polynomials, monomials are polynomials, and then when you have expressions that have like a plus or minus in there also. So for example, 8.5, we're going to follow this model just to recall back when we multiply two fractions, we divide out the common factors, but we can actually reduce any factor like on a diagonal, right? We don't have to have it right up on top of each other. So if we have 10 over 9 times 21 over 25, this is where it was split apart. The 10 was made 5 times 2 and the 9 3 times 3. The 21 was 7 times 3 in the numerator and 5 times 5 in the denominator. And so then what they did was just, slash out what's common. So there's a 3 here and a 3 way over here. You can do that as long as you're just doing it once and not double dipping. Okay, and with that 5 and the 5. So that reduces down to 14 over 5. Now, a lot of times we don't break it apart like that when it's numbers, but when it is a trinomial or something more, we need to break it apart and factor it out and see the different pieces. Now, these are just monomials, so you can probably do that one right on your own as classwork. And just go ahead and reduce that. So I'm going to write that out. I'll write out the steps as a review. Okay, so I just broke it apart. I dealt with the numbers first. So I had a 6 over 3 gave me the 2. 10 over 5 on the diagonal gave me a 2, so that I'm left with a 4. Then I multiplied my variables out here on the top. I did x to the 6th. And then y to the 5th, because remember you're adding exponents. Then I did x cubed times x squared in the denominator, got x to the 5th, and then just leave that y to the 7th. Then I applied the quotient rule. You could have done it in the reverse, that would be fine. And I get, or I'm subtracting my exponents, I get 4x in the numerator, and then y squared in the denominator. Again, here's like a little review here. When we divide fractions, we're actually multiplying by the reciprocal, and the same principle holds that once you multiply it, then you can simplify, right? We don't want to simplify at this stage when it's a division problem. You definitely have to flip. So the same holds true when you have a monomial divided by a monomial. You have to write it out carefully first. So we're going to write it as 45z to the 4th over 7y times the flip 21y squared over 5z. So don't forget to do that, whether it's just a monomial divided by a monomial or polynomials involved. So now we're going to reduce on the diagonal. So I have 45 over 5 leaves me with a 9, and then 21 over 7 leaves me with a 3. So I'm going to multiply out the numbers. 9 times 3 is 27. And then I have a z to the 4th y squared in the numerator after I multiply, and y over z in the denominator, or y times z in the denominator. So now I'm going to reduce those. I would get 27y over z, or not over, but times z cubed, because I have that z to the 4th over z to the 1st. Don't forget that that's to the 1st. So our answer is 27yz cubed. Okay, just a couple more things. We have multiply and divide rational expressions with polynomials. Again, don't reduce terms, only factors with factors, okay? So I'm just going to have you do one of these with me just to see how it goes. Again, I'm not going to test you heavily on any of this. We're really tight at the end of the term too. This is kind of a shortened up term. So I just want to introduce this to you. We do work with it a lot in Math 140. So on this one, we are going to factor first. So we have x squared minus 9 would be x plus 3, x minus 3, difference of 2 squares, all divided by x squared plus 5x plus 6. So that's going to be x plus 2x plus 3 should work. Just double check. 2x times 3x. Or plus 3x gives me the 5x. That's good. And then I have times x plus 2. And then in the denominator, I have 2 times 3 minus x. So I have that kind of reverse situation there, similar to what I had earlier. And now I'm going to reduce anything that's the same. So x plus 3 over x plus 3 gives me a 1. X plus 2 over x plus 2 gives me a 1. And then I have this x minus 3 over 3 minus x. Not a 1, but a negative 1. Okay, so all that I'm left with is 1, or negative 1. So I'm going to put that on the outside. Negative 1 over 2. So that really reduces down. But I need to keep in mind I have my domain is all real numbers such that x is not equal to, I can't have a -2, I can't have a -3, and I also can't have a +3 by this one here. One thing I want to just do is put these in numerical order. So I'm going to switch it around as -3, -2, and +3. Okay, and that's my domain. You're not asked to do that here, but I just going through this with you and pointing out, just planting those seeds for you. Now we're going to skip way up, just skip all this stuff. And we're not even going to work through that. One thing I just want to point out is that we can add and subtract rational expressions. You've done this before with just numbers, but if we do it with polynomials, we need to have a like denominator, just like we would with numbers. In this case, we do have a common denominator already, so we can just go ahead and add. And we keep the denominator, x plus 5, and we add the numerator. So the numerator would be x squared minus 42 plus 7 minus 2x. Now we do need to be careful if we have a subtract operation that we need to have parentheses in there, but this is plus, so we're okay. We don't need it. And now we're going to just simplify. So we're going to simplify the numerator to be x squared minus 2x minus 35, all divided by x plus 5. So we also want to track here that x cannot equal -5. That's our domain. But we can, looks like we can probably simplify this. So if we then do this, x plus 5 times x minus 7, does that give us our top number? We would have 5x minus 7x gives us the -2x, all divided by that x plus 5. We can reduce, and our answer would actually be x minus 7, but remember x cannot equal -5. Okay, so it actually turns out to just be a linear expression with a hole in the graph. So one more, I just want you to try this one for classwork, and then we'll be done with rationals. So when you look at this, it already has a like denominator. It's a little trickier to get it to have a like denominator. We'll do that in Math 99 later. So pause the video and try it. If you want to just follow along with me, that's fine. So we're going to have 9x plus 1 minus, with parentheses, 6x minus 2, all divided by x plus 1. So now we're going to distribute that negative. So we have 9x plus 1 minus 6x plus 2 over x plus 1. And that's all going to come out to 3x plus 3 over x plus 1. And then again, we can reduce 3x plus 1 over x plus 1. We have to factor first. Don't be tempted to just slash things out. And then we get a 3. But what is our domain on this? Our domain would be x not equal to 1, -1. Okay, because we would have x plus 1 not equal to 0, x not equal to -1. So we're tracking that. All right, so that's it for the chapter 8 stuff. And I'll just touch on a little bit of chapters 9 and 10 as well. So have a great day. Thanks for watching.